All right, I'd like to summarize a little bit of what I would like you to notice from the last example. So first thing is just sort of a definition that I think we've probably already said, but acceleration is defined to be the instantaneous rate of change in velocity. So I would like us to very clearly state how we calculate A of t from V of t or from S of t. So if we start from S of t, if we take one derivative to the limit as h goes to 0 of S of t plus h minus S of t all over h, we would get S prime of t. And S prime of t is the same thing as V of t. The derivative of your position function is your velocity function. If we apply the limit definition to this S prime of t function that we found, so we take the limit as h approaches 0 of S prime of t plus h minus S prime of t all over h, we get the second derivative. This is S double prime of t, which would be the exact same thing as if we took the limit definition and applied it to V of t and got V prime of t. And this rate of change, this instantaneous rate of change of velocity, is acceleration. So this is a really important relationship that we're building up here. It's one that we use to help us make sense of derivatives often, and it's also one that we use as we start trying to make sense of antiderivatives. So we want to keep track of this. Okay, now I want to summarize some things that I hope we noticed on the graph. So let me try and put these two side by side. We're going to try and fill in this table. So on the right, I have my three functions. I have S of t, I have S prime of t, and I have S double prime of t. And I would like to just notice some things about the graph. This is not anything that's tied to the fact that we're talking about a position function, a velocity function, and an acceleration function. So these are more general observations about graphs of functions, their derivatives, and their second derivatives. So first I want to relate function v back to function s, remembering here that v is s prime. So we're relating the derivative back up to the original function. And if v is positive, that's just about always true about this graph. So v is positive all through here. Just on the ends, it equals 0. And if I relate that back up to the original function, what that tied to was positive values of v are positive slopes, which means the original function is increasing. If v is negative, I don't have any of that, but this is a first derivative. So if v was negative, that would relate to the function decreasing. And if v is 0, I do have a little bit of that. In particular, this is a nice stretch to look at. Here is v equals 0 on the middle graph, and up on the top, what that meant was that the position function was constant. Okay, next we're supposed to relate the acceleration function back to the velocity function. So for this one, I want us to be thinking the relationship between v and a is that a is the derivative of v. So if we notice over here, see if I can get what I want, what are we starting with? Acceleration, a is positive, so that's this stretch right here. When a is positive, this original v function was increasing. All right, when a is negative, I do have a little chunk of negative. It's right here, and that lines up with when my velocity function was decreasing. And then last thing, when a is 0, what's a color we'll use? Blue. So here a is 0 and here a is 0. And if we compare that back up to the graph above, what's true about both of those pieces is that their slope is 0. So this is going to be, again, constant. So notice this looks exactly like what we set up above, and that's not a coincidence at all. If you think about this, we're starting with S and comparing it back to S prime. I don't know why I lined up above that. And then down below, we're starting with V and comparing it to V prime. So if we're talking about any function, it doesn't matter if it's position or velocity or something completely unrelated, if we take a single derivative, it's always going to be increasing, decreasing, constant related to positive, negative, 0. The one that's new and maybe a little more interesting is comparing A to S. So A is the second derivative of S. So now we are not one derivative apart. We're not necessarily talking about a slope relationship anymore. So if we look at where A is positive, so back here that was my pink highlight, that's this first stretch of the function. So this stretch right here, I'm going to highlight them all first since this isn't looking back just at slopes like we did before. When A is negative, that was the green down below, that lines up with this chunk of the graph. And then when A is constant, that was, oh, I shouldn't have used blue. I should have used pink for that first one. Here we go. Okay, we'll use blue for this. That's this stretch and this stretch. Okay, so what you may or may not notice, but we'll get good at hopefully as we go, is that what it's actually dictating is whether the graph's getting steeper or less steep, and this is concavity. So this part right here is concave up. This part right here is concave down. Another way to say that is slopes are getting bigger, and over here, slopes are getting smaller. So that's what I want us to try and look at here, and we'll keep practicing it as we go. So if the second derivative is positive, the function will be concave up. If the second derivative is negative, the function will be concave down. And if the second derivative is 0, what we should be seeing is that it's not bending. So we have a stretch where it looks like a straight line with a positive slope, and we have a stretch out here that looks like a straight line with a slope of 0. But what's the same about both of those is they look basically like a straight line. So it should be linear. And sometimes that happens just for a single instant instead of a whole stretch, but that's the idea that we're looking for. Okay, so we'll definitely dig into that a little more, but I just wanted to observe that from the graphs we already have.